Okay, perfect. So welcome everybody to this first seminar in the Hipparcos astro-seminar series. We will start having these seminars once per week. It will be on Wednesdays or on Fridays, depending on the preferences of the speaker. And well, we will send you the invitations every week. And for this first seminar, we have here Jonathan Freundlich, that is a researcher now in the Observatory of Strasbourg. Jonathan did his PhD on the Observatory of Paris under the supervision of François Combes. And after that, moved to Israel to work in the Avishai Dekel group. And also, well, also with me and other postdocs that we were there in these times. And after this adventure in Israel and Jerusalem, he moved to the Strasbourg, that is in where he's working now. And he will give us a short description of his work. That is the theoretical part, not the observational part. Although, Jonathan, I think you started with observations most of the time in your PhD, and you move it to theory, and is what you are working mostly now in Strasbourg. And well, basically, you will present today this theoretical part of your work, and probably in the future, in some other seminar, you will present us also the observational part. So if I think I haven't missed anything of your CV, so if I missed something important, please add it yourself now, and as soon as you want, you can start with the seminar. Okay.
Okay.
And thank you everybody for coming.
So thanks a lot for the introduction and for inviting me to talk in this very first Hipparcos seminar. I'm very happy to be here also with you, Santi, since it reminds me of the time you were in Jerusalem. And so, yes, I'm now a postdoc at the Observatoire Astronomique de Strasbourg, and I'm trying to work both on observations and theory. But today I'm going to focus on the theoretical side, and more specifically on the interaction between dark matter halos and the galaxies within them. So the work I'm going to present has been carried out in collaboration with different persons, in particular with Avishai Dekel and Fangzhou Jiang at the Hebrew University in Jerusalem, but also with Amrel Zant from the British University in Egypt and François Combes at the Paris Observatory, with whom I did my PhD. Maybe one question before I start, because how much time do I have?
Oh yeah, that's true. You have 45 minutes more or less,
okay.
And then we will have 15 more minutes for questions.
Okay, perfect. And also, please don't hesitate to interrupt during the talk. I don't mind at all. This is the way it's often the case in Israel, so don't feel shy. So to start with, I would like to remind a few things, recall a few things about galaxy formation in the lambda CDM model of structure formation. So as you probably all know, in the lambda CDM model of structure formation, about 26% of the total matter and energy content of the universe is called dark matter, 5% being baryons or ordinary matter, so which means that about 85% of the total matter content of the universe is made of dark matter. That means that at very large scales, structure formation is driven by dark matter dynamics with the cosmic web that you can see on the bottom picture. While at some point, baryons decouple from dark matter as they can cool, contract, and condense at the center of more diffuse dark matter halos. So you can see here a cartoon of a halo or of a galaxy within the halo with gas being accreted towards the center of the halo, towards the galaxy. This gas is potentially cool and can cool down. And by cooling down, it can form stars. And the stars themselves are also at the origin of strong feedback processes. So feedback processes is a term that describes different processes in the sense that throughout their lives, stars emit strong radiation fields, stellar winds, and then also explode as supernovae, which altogether contribute gas and hence to hinder subsequent star formation. So it's a feedback process in which star formation hinder subsequent star formation. And not only stars can be the cause of such feedback processes, but also active galactic nuclei at the center of galaxies that can also contribute to heat up or expel the surrounding gas. So the lambda CDM model of structure formation is extremely successful at explaining the very large scale distribution in the universe, the cosmic microwave background. I'm not going to come back to the successes of this model, but it has been facing some challenges at galaxy scales, precisely where baryons are dominating in terms of mass budget. So one of these challenges is the Q-score discrepancy. So namely the fact that if you look at dark matter only simulations, you see relatively steep profiles for dark matter halos. So this is the density profile. So the density as a function of radius. And dark matter only simulations predict profiles that are well described by this formula, the NFW, so-called NFW profile, as the dotted line here. But observations, on the other hand, favor more shallower cores, as can be seen here for dwarf galaxies, with a relatively flat density profile at the center. This is not necessarily in disagreement with lambda CDM, since the NFW profile is a prediction of dark matter only simulation. And in fact, when you introduce baryonic feedback, baryonic processes such as cooling, star formation, and feedback processes in the simulations are able to recover cored dark matter density profiles. And this can notably be seen in this simulation by Governato 2012, where the dark matter density profile evolves from an initially cuspy halo to a final cored profile. More generally, there seems to be a variety of halo response to the introduction of baryons in simulations. And this can notably be seen in these two plots in terms of the inner slope of the density profile and in terms of the concentration of the dark matter halo. So the concentration is simply the virial radius of the halo divided by some characteristic radius. For the NFW halo, it would be, as you could see in the previous expression, this RS radius. So as you can see in this plot, in the upper plot, when the stellar mass is relatively small, the inner slope follows what would be expected for an NFW halo. But for a specific mass range, for stellar masses between 10 to the 7 to 10 to the 9, there is a flattening of the density profile that can be seen in the red points here. And at higher mass, again, slopes that are more akin to the NFW slope, or even steeper due to adiabatic contraction. And so this can be understood in terms of a competition between the potential well of the halo and feedback processes, in the sense that at low mass, you have mostly what you expect from dark matter only simulations, while at some given mass, feedback processes start to become important, and that means that they can expel part of the gas from the halo and potentially to expand the halo, while at higher masses, the potential well is too strong for outflows to be launched, and thus the slope is again relatively steep. And so the adiabatic contraction that happens here, namely the fact that when you have baryons at the center of the dark matter potential, they steepen the potential well, and in turn, the dark matter is going to be attracted and to fall towards the potential, and thus the slope will become steeper. And the concentration is also steeper at high stellar to halo mass ratios. So the first question that I'm going to try to address in this talk is how to parameterize dark matter halos, in the sense that I've just shown that there is a variety of dark matter halo responses to baryons. And there has been quite some efforts to try to describe this through analytic formula, try to explain why these shapes. And so here are some known parametrizations of dark matter halos. So the NFW halo at the top that describes only cuspy, steep dark matter density profiles. Chord profiles can be notably described by a Burkett profile. And finally, parametrizations that enables variable inner slope, and thus to describe both cusps and chords. So all of these parametrizations are not equivalent in the sense that some of them have one shape parameter, the concentration for these halos. Some have more shape parameters. Some allow different analytical formulae. So here I wrote the different analytical quantities that we may want to have for studying a halo or a galaxy. So the concentration, the enclosed mass, the velocity, rotational velocity, the velocity dispersion, the gravitational potential. Sigma and sigma bar are the projected surface densities that can be useful for lensing, and f of e is the distribution function. So as you can see, many of these profiles do not have analytical expressions for all of these quantities. And finally, another interesting thing that we can be interested in is how, like, if we can parameterize these the shape of a dark matter halo in terms of the stellar mass or halo mass. So for example, there is a strong relation between the concentration and the dark matter halo mass for the NFW profile in dark matter only simulations. And there have been some other prescriptions to express the shape of a dark matter density profile as a function of the stellar to halo mass relation. And so in the first part of the talk, I'm going to present an alternative parametrization of dark matter halo profiles that is a specific case of the alpha, beta, gamma profile, but with fixed, some of the parameters are fixed. And as you will see, it provides a relatively good fit to both cusps and chords, actually better than the generalized NFW profile and better than the ANASTO profile. And it allows quite a number of analytical quantities. And finally, it can also be expressed in terms of the stellar to halo mass relation, which can be useful to fit rotation curves, for example. The second question that I'm going to try to address in this talk is how exactly do baryons affect dark matter halos, in the sense that, as I said in the beginning, when you put baryonic processes in simulations, you are able to reproduce chord dark matter density profiles, but with complex hydrodynamical simulations, you do not necessarily understand exactly or specify what are the exact physical processes at stake. Baryons can affect dark matter in different ways, all through the gravitational potential, since dark matter only interacts gravitationally. So one of these ways is adiabatic contraction. So I already talked about adiabatic contractions. So namely, when baryons fall at the center of the halo, they steepen the potential well, which in turn attract and make the dark matter contract in an adiabatic way, because dark matter does not radiate energy away. A second way for baryons to affect the dark matter is through dynamical friction, in the sense that if you have a satellite galaxy or a clump of gas that is moving with respect to the dark matter background, it will lose parts of its orbital energy to the dark matter background. So it's dynamically heating the dark matter. And this can contribute to form cores, as was shown by Amrelsant in 2001 and 2004. And finally, and this is what I'm going to focus on, when you have feedback processes in a galaxy, you can move significant amount of the mass at the very center of the halo. And since you move mass at the center of the halo, you also change the potential. And thus you can have repeating potential fluctuations. And this can notably be seen in these two plots from simulation by Ponzen and Governato, where on the left panel, you can see the baryonic mass fluctuating as a function of time within the halo at different radii. And on the right panel, you can see the effect these mass fluctuations would have on test dark matter particles. And the net effect is that these test dark matter particles are slowly deviating from their initial trajectories, and this leads to the formation of cores. So that is the second part. And finally, the same process that contributes to expand the dark matter distribution could also contribute to expand the stellar distribution. And so I'm going to talk about ultra-diffuse galaxies, which is a type of galaxies that is characterized by stellar masses of dwarf galaxies and effective radii comparable to the radius of the Milky Way. So extremely low surface brightness objects. There were different scenarios that have been proposed to explain their formation. So they could have been failed Milky Way galaxies that stopped forming stars very early in their history, and hence their low stellar content. They could also be the high spin tail of the galaxy population, in the sense that they could reside in a halo that is rotating extremely fast, and hence make them, by the centrifugal force, extremely expanded. They could also be tidal debris or tidally disrupted dwarfs. And finally, as I just mentioned, the same process that leads to core formation, that may lead to core formation in dark matter halos, could also result in the expansion of the stellar population. And that was notably suggested in this example, a dwarf galaxy that has a relatively bursty star formation history here. And this bursty star formation history results in a bursty episodes of feedback and outflows that both make the stellar distribution expand. And so this is seen in these plots where you see the stellar surface density that evolves from a relatively sharp profile to a very extended profile. And at the same time, the dark matter distribution varies from a cusp profile to a core profile. So that was for the main questions that I want to address. And one of the tools that I'm going to use in this talk is the Niehaus simulations, which is a series of about 100 cosmological zoom-in hydrodynamical simulations with cooling, star formation, relatively strong feedback, and which has notably the advantage to resolve about 1% of the virial radius at each halo mass. That is for my introduction. Again, if you have questions, don't hesitate to interrupt me. But if not, I'm going to start with this density profile that we are proposing to describe dark matter halos. So you can see here the expression of this profile. So it has a slope at r equals infinity that is equals to 3.5. So it's slightly different than NFW at high radii. And then it has a variable inner slope and a variable concentration, in the sense that in this expression, you have two parameters, A and RC, so some concentration that is hidden in RC. And these two parameters can be related to the actual inner slope that I usually calculate at 1% of the virial radius in this talk, because this is the resolution of the Niehaus simulation, so which I called S1. And C2, which is the concentration corresponding to a characteristic radius where the slope equals -2. So I define the concentration in the same way that it is defined for NFW halo. And so I can compare both together. So we applied this formula to simulated dark matter profiles, so both cusps and cores, and compared it to the ANASTO and generalized NFW with variable inner slope, as you can see here. And the main result, so this is in terms of the density, and in the next plot here, it is in terms of the rotation curves. And in fact, the fits are better than both ANASTO and generalized NFW, especially at the very center of the rotation curves. That's the first point. We are able to have at least as good and even better fits than the more common generalized NFW and ANASTO. Then the second thing that I'm not going to go too much into the details, but which was shown in the beginning when I first talked about this profile, is that we have quite a large number of analytical quantities, so which can be useful to speed up computations and to use in models. And finally, we can express the inner slope in the profile and the concentration in terms of the mass. So that means that, as you can see in these two plots, on the left panel, this is the inner slope compared to the inner slope of NFW profile. And on the right panel, it's the concentration, again, over the NFW concentration, just to look at the differences between the two. And what you can see in these plots is that you have a flattening of the halo compared to NFW in a specific mass range here. Again, here it becomes steeper because of adiabatic contraction. And this effect is also seen in the concentration parameter, which is actually something relatively new, since these kind of curves have been obtained quite regularly in different types of simulations. But in general, we don't necessarily see an effect of the more global concentration parameter, so which reflects the response of the halo as a whole to the introduction of baryons. And you can see here a 20% drop in this concentration, again, in the same mass range where core formation occurs. So we provided fitting functions for these two curves, and this enables to have a mass-dependent profile. So that means, of course, there is some scatter, but that means that if you know the stellar mass and or the halo mass of a galaxy, you can predict what should be the shape of the dark matter halo of this galaxy, at least if you believe the simulations. So from these prescriptions, you can predict what is the shape. And so in these plots, I use these predictions for the inner slope to fit rotation, like to fit the density curves and the rotation curves. And these are the fits, and we compare it with another profile that is widely used in the literature to fit rotation curve, which is the Dicintio 2014 profile. And we found that our parametrization was about as good as the Dicintio profile, again, with one relatively important advantage, which is that this profile is largely analytic. So which means that if you want to use analytic functions, either for modeling or for speeding up calculations, it's useful. So this is my first conclusion about this parametrization of dark matter halo profile. So we propose a new parametrization of dark matter halos, which describes both cusps and cores with a flexible inner slope, variable concentration, and it has analytic potential, velocity dispersion, and lensing properties. So it has only two shape parameters, inner slope and concentration. It's generally better than generalized NFW and ANASTO. We observed the halo expansion for a specific mass range, and it can be treated as a mass-dependent profile as good as existing mass-dependent profiles in the literature. And so as such, can be applied to different things, to model observational rotation curves, to parameterize gravitational lenses, since we have analytic lensing properties. And it can be used as initial conditions for idealized simulations to model the cusp-core transformation, and I'll talk more about it just now. And finally, to be implemented in semi-analytic models. And this is also something that I'm going to evoke later. So as I recall, you have quite a large number of analytical formula for this profile. Not everything, of course, and not always in simple functions, especially for the lensing properties, but it's still a significant advantage compared to other parameterizations. Okay, so now I'm going to talk about the second part of what I presented in the introduction. So namely, how can we model core formation in dark matter halos? So the objective here is to try to understand a bit better through physical processes and analytical modeling, how baryons can affect dark matter halos. And I'm going to present two models to describe this. So the first model, in the first model, we assume that the effect of feedback is that of major outflows in the galaxy. And so major outflows means relatively large mass changes at the center of the halo. And what we're going to model is, the effect that sudden mass change has on the shape of the dark matter distribution. So for that, we will assume that we have a halo that is initially at equilibrium, and we will follow spherical shells of dark matter, spherical shells enclosing a given dark matter mass at different radii in the halo, when a mass is added or removed at the center. So mainly removed, since we want to talk about outflows and expansion. So if the mass change is slow, this is something that we know, then we can assume that angular momentum is conserved on circular orbit, and there is a relatively well-known formula that relates the final radius of the shell to its initial radius, and it depends on the ratio between the mass that has been added or removed at the center and the mass enclosed by this given shell. So this is adiabatic contraction or adiabatic expansion. But what we want to describe here is not a slow mass change, it's rather a rapid, violent outflow that happens on a time scale that is much shorter than the dynamical time of the halo. So what we assume here is that we have a halo that is initially at equilibrium with some distribution of stars and gas. And if we look at the shell, its energy, it's given by the sum of its potential energy and the kinetic energy. And since it's at equilibrium, the kinetic energy is set by the Jeans equation, so hydrostatic equilibrium of the halo. But now what we assume is that we have a sudden gas removal, and we do an impulse approximation. So namely, the potential adjusts instantaneously to the mass change. And so we have this additional term, but the kinetic energy remains the same, in the sense that the velocities remain frozen to their initial values. And finally, so in this case, the system is in some kind of hypothetical transitional state out of equilibrium. And then we assume that the system slowly relaxes to a new equilibrium where we have, again, the mass of the center that has changed, but now the kinetic energy has adjusted itself to the new mass distribution in the halo. So this KF is again set by the Jeans equilibrium in the halo. And the core assumption of the model is that the energy is conserved for these shells during the relaxation phase. And so if we have parametrization for the potential and the kinetic energies, and we do have, in particular with the profile parametrization that I just presented, then we can express energy conservation between this hypothetical transitional state and the final state of the halo of each cell, and to deduce and predict what would be the evolution of the dark matter density profile. So we tested this on the Nihao simulations, and we found that it was successful in about 75% of the cases when we were excluding major mergers. And we have all the reasons to exclude major mergers, since we are not attempting to describe this kind of occurrences. And thus, this is the idea of the model, and we still need to test it on ideal simulations. So this is something that I hope to be able to present some other times. An interesting application of this model may be to explain baryon-dominated galaxies at high redshift. And so there has been some claim recently, notably by Reinhard Genzel and his team, that galaxies, massive galaxies at redshift 2 had extremely low dark matter fraction. And so this may require a mechanism to expel or expand part of the dark matter from the center of the galaxy, while at the same time bringing baryons inside. And what could enable this is precisely these bulk outflows, but in this case, not from star formation, but most probably from active galactic nuclei in these massive galaxies. And in fact, it could be combined, because the problem here is that it's relatively early in the history of the universe. And so that means that you need a process that is sufficiently fast to explain core formation at relatively early time over a time scale that is quite short. And so you want to have a particularly efficient core formation process. And so what we're currently working on is the combination between dynamical friction, which heats the halo, and this the effect of this bulk outflow process. And in fact, when the halo is preheated, we find that the effect of feedback will be even more pronounced, and that may provide the mechanism to have cores at early time in the history of the universe and core formation that happen on relatively short time scales. So this is what you can see in this plot, the difference of one feedback effect. So this is runs of the model that I just presented. On one case, in a halo that is not preheated, and you see that there is a small change because of the outflow. But if you preheat the halo because with dynamical friction, then you can have a much more efficient core formation. So in this first model, we were trying to explain core formation from bulk outflows. But in fact, feedback could also be described not through bulk outflows, where massive changes occur, but by small changes in the baryon distribution. And this is notably seen in these plots, which is from the simulations of the SILK project, which shows the effect of feedback processes and supernova explosions on the interstellar medium. And you can see that you have fluctuations at different scales of different amplitudes, and thus that the feedback processes result in fluctuations in the density of the interstellar medium. And so these small fluctuations could also affect the potential, so leading to small potential fluctuations, and these small potential fluctuations to affect dark matter particles. And so with Amrel Zandt and Françoise Combe, we developed a different model where we assumed that the effect of feedback was to have stochastic density fluctuations in unperturbed homogeneous medium. We separated these fluctuations in Fourier modes. And so in some sense, each of these Fourier modes of different amplitude and different size induces a kick, a force kick on test dark matter particles. Each of these kicks is very small, but cumulatively, they can induce the dark matter particles to deviate from their trajectories in the same way that two-body relaxation enables particles to deviate from their trajectories in a diffusion-like process. So this is the cartoon where you have these density fluctuations at different scales, different intensities, some negative, some positive, and the radius of a test dark matter particle that slowly does a random walk away from its initial orbit, and is basically, the test particle is basically dynamically heated by the fluctuations. And so we did some idealized simulations that showed that this indeed led to the formation of a core in initially cuspy dark matter halos, thus validating this idea. And we still need to try to bridge the two models that I presented. In fact, the second model had a relatively unexpected application, which is related to fuzzy dark matter. So I don't know if you heard about fuzzy dark matter. It's a pretty exotic theory for dark matter. It has many names. It is sometimes called ultralight dark matter, scalar field dark matter, wave dark matter, or Bose-Einstein condensate. And the main idea here is that dark matter is not made of cold, massive particles like WIMPs in the standard model of cosmology, but instead is made of extremely light particles, axions, and that since these particles are so light that their de Broglie wavelength is actually of the scale of a kiloparsec. So that means that the particles have quantum properties at the scale of a galaxy. And so because of the large de Broglie wavelengths, you do form cores naturally because of the Heisenberg uncertainty principles, in the sense that you cannot condense these quantum particles at scales smaller than the de Broglie wavelengths, at the scale of the kiloparsec. And another effect of this exotic theory is to have large interference patterns at very large scales, that you can see here in this plot. It has, the halo of this kind of dark matter has a solitonic core and a very peculiar bump in density distribution. And finally, it also presents density fluctuations inside the halo, which is again due to the uncertainty principles in the sense that you have quantum fluctuations at a kiloparsec scale. So I agree, this may seem a bit far-fetched, but it's a theory that is not totally excluded yet. And some people actually used the model that we developed with Ramel-Zandt to try to constrain this model. The idea being that in our model, we were describing how fluctuations from baryons were affecting dark matter particles and dynamically heating dark matter halos. But if you reverse this, if you have density fluctuations from the dark matter, you're also going to heat up stellar systems. And in particular, there is a stellar cluster in one of the dwarf galaxies around the Milky Way, Eridanus 2, which could have been heated up if you had these fluctuations due to the fuzzy dark matter. You would expect the stellar cluster to be heated up and thus and to be more expanded than what you see today. And so by looking at its size and looking at the age of the stars in this cluster, you can constrain the possible dark matter, fuzzy dark matter masses that are allowed by this observation. So we looked at the calculations. Actually, we redid these calculations, but in a more rigorous way from the Schrödinger-Poisson system. So the combination of the Schrödinger equation and the Poisson equation for gravity that describe the halos of fuzzy dark matter particles. Currently, investigating the effect of these fluctuations on galactic disks, in the sense that there are two things on galactic disks that we expect, which is on one side that it may affect the strength of the bar, and it's actually diminishing the strength of the bar, and it's also going to expand the thickness of the galactic disk, and so this is something that can also be used to constrain this model. There was some interest again in this model recently because it may be possible to rule it out relatively easily, but so far it's not totally ruled out. And finally, the last object where it could be interesting to constrain this model is the stellar streams observed in the stellar halo of the Milky Way. And so you are probably aware of these objects that are extremely thin streams of stars observed in the halo. And again, if you had these fluctuating dark matter potential, you would expect these streams to be potentially heated up or deformed by the fluctuations. And from their very small thinness, you may be able to constrain the fuzzy dark matter particle mass. So in this second part, I presented two models for core formation. One model invoked bulk outflow episodes, and the second model invoked small stochastic density fluctuations. So both were tested again, different types of simulations. In the first model, we're still planning to do some controlled experiments, simple simulations. It may be able to explain core formation at high redshift. And the second model, we're currently trying to look at its consequences for fuzzy dark matter model. And so this leads me to the last part of my talk. I guess I still have 5-10 minutes, which is about the formation of ultra-diffuse galaxies. So ultra-diffuse galaxies are extremely low surface brightness objects that have been observed for a long time, but that were kind of rediscovered in 2015 when we had instruments that could observe more of them, in particular in clusters. And there has been different questions about ultra-diffuse galaxies, which is whether they're indeed distinct from the overall galaxy population. So this, it seems that it's not the case. There is a large debate about the mass of the dark matter halos in which they reside. And finally, something that I already mentioned, the question of their formation, whether it's failed Milky Way-like galaxies, the high-spin tail of the galaxy population, tidal debris, or resulting from outflow episodes from stellar feedback. So with Fangzhou Jiang, we looked at the ultra-diffuse galaxies in the near-House simulations to try to see if we could constrain these formation mechanisms. And what we saw was that there was a relatively narrow range in stellar mass and halo mass for these ultra-diffuse galaxies, that they had average halo spin. So at least in these simulations, they are not the high spin tail of the halo galaxy population. They do have a slightly lower concentration, a high dark matter fraction, stochastic index close to 1, which is what is observed for UDGs in general, average velocity ratio, and high cold gas fraction, and a wide range of specific star formation rate and color. And all of this pointed towards, in fact, these isolated ultra-diffuse galaxies being formed by the same process leading to core formation. And indeed, when we look at the core, the profile, dark matter density profiles of UDGs in these simulations, we see that a striking feature is, in fact, that UDGs in the Nihao simulations have cored dark matter density profiles. So again, more quantitatively indicating the relation between both the extension of the stellar distribution and the extension of the dark matter density distributions. And so we're currently looking at trying to describe this better, and in particular in trying to relate the shape of the dark matter density profile with the burstiness of the star formation history, in the sense that in the models that I presented, we expect to have a correlation between the two, bursty star formation history leading to bursty outflow episodes, and hence to more effect of feedback. And this is what we seem to see here. So we defined a burstiness parameter, which is a contrast parameter describing how contrasted are the fluctuations over a given time scale in the star formation rate history that we see here. And so if you look at a given time scale, let's say here, you can see that the galaxies that are the most bursty, so there is the highest B parameter, are also those that have the lowest inner dark matter density slope. So which kind of show the correlation in these simulations between the two. I'm always saying in these simulations, because I think there is a strong caveat that feedback is extremely strong in Nihao, so we may be biased towards observing effects of feedback when other simulations may have different feedback implementations and may see different things. But this is what we see in this suite of simulation. We also looked at a group of galaxies that is a Nihao-like group simulated by Aaron Dutton in 2015 to try to look at UDG formation in galaxy groups and clusters, in fact, in cluster. So what we see here is that we have some galaxies that are UDGs at inflows. What I show here are different quantities related to a satellite galaxy. Red correspond to areas where the galaxy is a ultra-diffuse galaxy. And so in this case, it's a ultra-diffuse galaxy from the beginning, and it's disrupted at some point inside the cluster. Here is another example where you have a galaxy that is a UDG at the beginning, but which survives. And finally, an example where you have a galaxy that was not a ultra-diffuse galaxy when it fell onto the cluster, but which became a UDG after pericenter passage. And so what is striking here is that at pericenter passage, you have dark matter loss, slight dark matter loss here, gas removal, so due to RAM pressure stripping, and at the same time, size growth and an increase followed by a decrease of the kinetic energy, which is significant, which is indicative of tidal heating. And so in this case, we observe that in this galaxy cluster, about half of the galaxies of the UDGs were already UDGs at inflows, so most probably formed from feedback outflows, while about half of the UDGs were formed by tidal puffing up at pericenter. So it gives a different answer. And so in the Nihao simulations, actually in the mass range where we have UDGs, we mostly have only UDGs. And so we do not form compact dwarf galaxies, and which is potentially a problem for the simulations. And so to do that, Feng Jiang maybe I won't say too much about it because I think he's also going to present to you things soon. But he developed a semi-analytical model to describe the satellite galaxies inside halos. And in this model, he notably implemented the parametrization of halos that I showed you before. So this model takes into account dynamical friction of the satellite, ram pressure stripping, and also tidal effect, and potentially the effect of the mass loss of the satellite as it goes through the cluster, the effect it has on the shape of the dark matter profile. And here I think this is an interesting application in the sense that in this case, you see the dark matter density, the response of the inner slope of the dark matter density profile as a function of the stellar to halo mass ratio. So I've already shown these plots. And for the Nihao simulations, you have this curve, the black curve that I showed before. So core formation in a specific mass range in this simulation with strong feedback. But in fact, in other simulations where feedback is not that strong, the response can be flat. And in this semi-analytical model, it is possible to implement these relations in the model to see the effect it has, the effect this dark matter halo response has on the observable characteristic of satellite galaxies. And in fact, this is what we're currently doing here, which is namely that if we implement this slope of resulting from high feedback simulations in the semi-analytical model, we form a large number of ultra-diffuse galaxies. So when the halo responds by forming cores in a specific mass range, we end up with a large number of ultra-diffuse galaxies and a very low number of compact dwarfs, which is also what happens in the Nihao simulations. And while here, when we implement a flat halo response, then we form more ultra-compact dwarf and less ultra-diffuse galaxies. And so this enables, with this semi-analytical model, to have more statistics on halos in general. I mean, on satellite galaxies to understand more what they do, because one of the problems is that it requires a very large dynamical range to simulate in simulations these kind of objects, while with this semi-analytical model, we can try to test different aspects. And in this case, we tested the dark matter halo response to baryons and saw that it had an effect on the nature, whether UDGs or compact dwarfs, and thus on the stellar extent of these satellites. So this is how the conclusion to this third part, which is that we looked at the formation of ultra-diffuse galaxies in the Nihao simulations, and we showed that in these simulations, in the field, UDGs are formed by a bursty star formation history that leads to repeated outflows from feedback, density fluctuations, and hence the stellar expansion of both the expansion of both the stars and the dark matter. And a consequence that may be testable someday is that field UDGs should have chord dark matter density distribution. And we also looked at the formation of UDGs in groups. So first of all, field UDGs can survive in clusters, but they can also form through tidal puffing up at the pericenter, together with the quenching of star formation due to ram pressure stripping. And so in the Nihao simulations, the UDGs are not characterized by specifically high spin, but they do reside in dark matter, in chord dark matter halos. And finally, we implemented a dark matter halo response in semi-analytical model that seems to confirm this relation between the dark matter halo response and the formation of ultra-diffuse galaxies. And so to end up on a different note, I also wanted to say that there has been some debate about whether ultra-diffuse galaxies could be a challenge to alternative gravity theories, and in particular to Mond. And this does not seem to be the case. But in fact, UDGs can also be a testing ground for specific effects of these theories. And I can tell more about it if you're interested. Thank you.
Okay, thank you a lot, Jonathan. It was a very nice presentation, very clear. I think we have many questions in at least for the two first parts, and then we can go for the questions that are also in the audience now. But the questions I am talking about are the ones in the chat, and if you want, I can read them, and then you can answer to each one of them. We have two. The first one from Felipe Llanes Estrada about the part one. He said that you state that the Deckel-Zhao profile provides a better fit to the simulations than the other profiles. But the question is if this is true, even considering that the parameters, this 1, 1/2, 3.5 that you are using are hidden parameters when you calculate the chi square. So if you leave these parameters free and you make the chi square, this is also true, this is better fit, or you need to use these specific parameters?
Okay, so so in fact, this profile is a specific case of the alpha beta gamma profile that was studied by Zhao '96 and also by Dixintio 2014. And so, in fact, one of the usage of the alpha beta gamma profile is sometimes precisely by leaving these three parameters free. And so, of course, if you leave these three parameters, so two more parameters free than what we have with this specific profile, then you will have slightly better fits. But the thing is that that would be at the expense of two more additional parameters and at the expense of analyticity, in the sense that for the Dixintio profile in general, all of the quantities are either non-analytic or or analytic with non-elementary functions. So this is shown here. So with the general case of a Dixintio profile, the only quantity that is analytic is the concentration, okay? And you can have the enclosed mass and the velocity that are expressed as a function of non-elementary functions here. But all other quantities like velocity, dispersion, and potential surface densities need to be integrated numerically. So depending on what you want, it may be a problem or computationally expensive. I think there is another side in this question, which is the fact that a particular feature of this Deckel-Zhao profile is that the outer slope is fixed to 3.5. And so this may mean that in certain situations, maybe clusters, I'm not very familiar about the literature in this regard, but I think that there has been some ongoing discussion about what was the slope at large radii of dark matter halos. And it seems, I think it's slightly lower, like it's higher than the 3 of the NFW profile, but it may be lower than 4. But I'm not exactly sure, but it means that this is something that is fixed here. And maybe if you're interested in the outskirts of dark matter halos, you would be less interested in this profile because you cannot vary the outer slope.
Related with this, Jonathan, wasn't this number related with some toy model developed by Avishai with a theoretical background? This is not from...
No. In fact, so the reason for these specific values is that there is this very nice article by Zhao, 1996. And I think this is what I showed here in the note. So Zhao showed that for this general alpha beta gamma profile, you have some specific values where you can have analytical quantities. So when alpha equals an integer, when beta equals 3 plus an integer divided by alpha. So it's, and so the profile that we're proposing is one of the simplest possibilities in this range of cases. So basically in our case, we have, okay, basically here beta equals 3.5 in our case, and n equals 2. I'm sorry, this is not alpha, it's I should have adapted, but basically this is b equals 3, like the case that we're talking about here, it's the small b equals 2, so which correspond to this alpha, in fact, sorry for that. And J equals 3.5, sorry, which corresponds to this beta. So you replace alpha by B and beta by J. And so basically we're in the case where K equals 1 and N equals 2, which is one of the simplest cases. And in an article in 2017, Avishai showed that was looking at another possibility, I think, with A equals 1 and B equals 3, I think. And it was not as good as what we're doing. So this is why we focused on this one, which is, if you want, the simplest Zhao profile that enables analytic, that works.
Great. We have a related question also by Octavio Valenzuela that asks if your profile fit captures the diversity of rotation curve shapes in galaxy population discussed in Oman et al. 2015. And if it does, what is creating the diversity in your case?
I mean, I've read Oman et al. 2015, but maybe I need a reminder because now I'm not sure about what it is, but I can answer to the second part of the question. The diversity, the way we understand this diversity in the Nihao simulations or in general is what I explained at some point, which is this competition between the depths of the potential well and feedback processes. Which in this case is already evoked in Deckel and Silk 1986. Namely the fact that if you have a dwarf galaxy, you don't have much star formation, you don't have much feedback, so the halo is mainly what you expect from a dark matter only halo. So that is shown here. I can also show it here in this plot. In fact, it's the same. So basically this ratio between the inner slope and the inner slope for NFW halo is equal to 1 at very low mass, behavior like in a dark matter only simulation. But at some points, when the baryonic mass increases, on one side, you have a steepening of the potential well, and on the other side, you have star formation and feedback processes. And in this mass range, the feedback processes become sufficiently big to expel part of the gas, and thus to contribute to these outflow events and also expand the dark matter distribution, while at the same time, the stellar mass is sufficiently small so that the potential well is not too steep, and so the outflows are able to be launched from the galaxy. And finally, at high mass, you're in the case where you could have feedback processes, but the stellar mass is too high and the potential well is too steep to allow strong outflows to be launched away from the galaxy.
Okay, thank you. And I have a very small and fast question also about this part, and then we will go to the question by Armando. Did you apply this model also to other dark matter only simulations, or you only use it the Nihao? Because you said, we know that Nihao has a very strong feedback scheme, so maybe the profiles can change when you use a more traditional feedback scheme from other codes. You have applied the profile to other...
So I did apply it to the Vela simulation that you know quite well, I imagine. And so it works well. But I think that to some extent, whatever the simulation code is, one of the first things that people are looking is whether like the halo shapes and the size mass relation, concentration mass relations are, what are these relations if they are compatible with other simulations. And so that means that I would expect that most simulations are going to converge on these relations and have relatively similar dark matter halo shapes. And so in this part, we applied it mostly to the Nihao simulations, but since the halo profiles are probably also quite comparable in other simulation suites, I would expect that it also works on other simulation suites. But of course, this can be tested, but right now, I would be more interested, in fact, to compare this to observations and to rotation curves to try to see what are these two parameters, so the inner slope and the concentration that we define for this parametrization, what can be inferred from observations, for example, observations of spiral galaxies in the nearby universe.
Great, okay. So the next question is by Armando Gildepaz and is for the second part. And he's asking, when studying the fluctuations in the galactic disk, do you still assume that the mass change is spherically symmetric? And this question is motivated because the outflows in the vertical are vertically stratified systems, like the galactic disk, happens mainly in the vertical direction.
Yes, so I think this is a very important question. So I think that the question referred to the first model where we model this spherical halo. And yes, here we are in a totally spherical case, and this is what we assume. We followed spherical shells in the halo. And I think that it is totally true that that outflows are usually not spherically symmetric, especially halos from AGNs and jets, etc., but also outflows from the disk that will flow mostly perpendicular to the disk. So that we're not taking into account per se in the model. But so I think that there are two things. On one side, I would expect that the fact that the halo itself is not spherical, that the outflows are not spherical, my intuition, I would say, because it may not be totally, I mean, I don't have necessarily all the evidence, but there is, in this regard, a very nice article by Andrew Ponson in 2015 that tried to study the cusp core transformation both in spherical halos and in non-spherical halos. So in this case, it was the non-sphericity of the halo. And it seems that when you have non-spherical halo, or maybe also non-spherical outflows, the cusp core transformation may be even more efficient than in the spherical case. So that's what I would expect. I don't have a very fine, like, definitive argument about this. This is definitely something that should be more studied. So that's one thing, that non-sphericity is going to influence things. And my impression is that it's going to enhance core formation. Second thing about this model, the fact is that the galaxy is relatively small compared to the halo. So the typical size of the galaxy is 10% of the virial radius. So here we're trying to describe the effect of a mass change that, even if it's not totally perpendicular, like not exactly spherical at the scale of the galaxy, when you look at it from the perspective of the halo, you're basically looking at a mass change at a very small radius at the center of the halo. And so in this way, maybe it may mean that the model could be applied, even if the outflow is not totally spherical at the scale of the galaxy. And the way that I implement in the model, we can implement a mass, like the mass change can have a mass profile, in the sense that, but the simplest way to implement the model is just to assume that you have baryons at the center, so neglect the size of the galaxy, and change the mass at the very center. In this case, it's just a mass change.
Okay, thank you, Jonathan. And now, if somebody else in the audience wants to ask a question, I let you to open the microphone if you want. You can do it yourself. So if you want to make some other question, please do it. You have time for another one. Well, okay. So if there are no more questions, then we can leave it here. Thank you a lot, Jonathan, for this very nice work. Three very nice different works in collaboration with people in Israel.
There is a question.
Yeah. Manzanilla Guerrero.
There is a question about Oman 2015, but the thing is that I don't have it in mind. So can someone remind me or us about Oman 2015?
Yeah, you can open your microphones if you want to. Oh, you cannot. I gave you permission, I think. Let me check it. Allow partitions. I think you are allowed to unmute yourself.
So for a given mass, you find different RC shapes. So, okay. Okay, so that means, so basically, if I understand the question, it's about the scatter in the relation, in the sense that if you look at a curve like this one, you have some significant scatter, and what can be the physical origin of this scatter. So I do not have an answer for that. I think that you can see the scatter already here. So this is the Nihao simulations. And I think that there are many different processes. Like for example, in these simulations and also in observations, there are many things happening in addition to feedback. It can be related to the accretion history and whether in the sense that satellites or incoming galaxies that are merging will have some effects, either through dynamical friction. As I said, dynamical friction can heat up the halo. That's one thing. Secondly, the incoming of satellites is also a mass change, although it's not spherical, but it's a mass change. So in the same way that you have mass addition, you could also have the result of this mass addition to the potential, and hence have either expansion or contraction of the halo depending on mass changes due to the satellites. The effects of the non-sphericity that I think are really difficult to describe. So these are some areas that I think can account for the scatter. So in large part, the accretion history, different star formation history, because different star formation history are going to lead to different feedback processes if you believe in these kind of models. So in the sense that if you have a more bursty star formation history, you would expect this model to produce more chord profiles, so have these points more down. And while if for some reason you have a galaxy that has been relatively quiet in terms of star formation in the last few gigayears, you would expect to have the cusp reformed and hence more something that is on the upper part of the scatter. So I don't know, maybe other people have other ideas, but I would like the two things that I can say to answer here. It's on one side, something that can be accounted for this model, which is the star formation history as a parameter that was induced more or less outflows. And on the other side, something that is not accounted in these models, which is the accretion of satellites.
Maybe I can complement. The interesting thing is that if this is true, you may find a clear correlation between star formation history or this satellite activity with the shape of the rotation curve, and this could be potentially tested observationally.
Yeah, I'd be happy to see that because it would also contribute to a test of these models to some extent.
Exactly.
Okay, I think we have another comment by Jorge Sanchez Almeida. Sorry,
Jorge. Thank you. So yeah, this is Jorge Sanchez Almeida, Jonathan. It's more a comment than really a question. We published a paper last year where we claim that the presence or not of cores is mostly a manifestation of the system to be in thermodynamic equilibrium. So that if the system, the potential is in thermodynamic equilibrium, you always get a core. And so what we show in that, I mean, this was already in the literature. What we show is that if you, I mean, the cores that are predicted are polytropes and all have basically the same shape, which agrees with the cores that are observing little things in this set of galaxies where people have measured with some precision the rotation curves. So in a sense, this tells us that first, that, I mean, from the shape of the density profile, I would not expect to be able to distinguish different mechanisms at which you form the cores, because in the end, all of them are going to produce the same, exactly the same density profile. And yeah, that was one thing. And at the same time, in these terms, the different ways in which you are producing cores basically are different physical mechanisms that allow the system to reach thermodynamical equilibrium. So if it is fast enough compared with the lifetime of the universe, then you get a core. If it is not, it's not efficient, then you don't. Okay. So that was my comment. Thank you.
Okay. Very interesting. Thanks.
Okay. So if there is some other comment. No, and okay.
So maybe just a question, the article that you were referring, Jorge, it's, you're the first author of it? Oh. I cannot hear, but if you can send me the reference, I'd be happy to look at it.
Okay, I will.
Okay, perfect. So we will need to leave it here. Thank you, Jonathan. Sorry, everybody, for the problems with the Zoom and with the muting or unmuting the microphones. It's the first meeting. Probably the next one will get a little bit better. Thanks, Jonathan, for the talk, and hope to see you soon and to hear more about your research. And thank you, everybody, for coming here in this first seminar. Just to tell you that next week we will have another seminar, same day, same time, by Professor Avishai Dekel from the Hebrew University. Okay, so thank you, everybody, and have a nice week and day.
Thanks to you all for listening.
No.
So was the sound okay during the talk?
Yeah, in some moments you were kind of various talking, various low, and then spinning fast just to reach you again. The Zoom algorithms probably do that, but we heard you very well in the entire presentation. So only very few moments it was not working well.
Yeah. Okay, good. Because